Hi, everybody. I'll start. I can see people coming in, but I'll start because I have literally so much to tell you. My name is Tim Ward. I'm an engineer out of Copenhagen, Denmark, in a company called CluedIn. Essentially, you could sum us up as a data integration platform. I myself have been using Neo4j for actually more close to 6 years now, as the rest of the engineering team has as well. I started on 1.6 of Neo, which is actually quite a while ago now. And if we have a look at the kind of status quo of the market right now, it kind of looks a little bit like this. Most companies in the room right now are either in the middle of this big data era, or actually maybe even getting to the end of it. And the irony of this with the customers and the companies we talk to is actually more and more companies are using their data less than ever before because of the sheer amount. It's probably also worth mentioning that a lot of the companies in this room are looking into how to utilize this and turn into much more data-driven kind of companies, also known as kind of this smart data era. And to understand how we can help companies become more data-driven, you need to know a little bit about what we do. So essentially what CluedIn does is we are an integration platform that helps companies become a connected enterprise. So very much following the same vision and structure that is given from Neo4j themselves. And the reason we do this is because if you look at the average company, they use anywhere from 30 to 70 to, with some of our customers, 350 different tools to solve things like sending mail and taking phone calls and customer management and project management and accounting and invoicing. I only stopped because I ran out of breath, but you can imagine the list just goes kind of on and on. And for us, we kind of saw this kind of trend in the industry with the amount of adoption rate of new SaaS products and the explosion of new tools that are available to companies. This is something that gets very tedious if you take a manual approach to this. So at CluedIn, what we do is we build a platform that automatically connects the data between these systems. And to provide a sophisticated tool like this, we need a sophisticated stack. So this is kind of a bird's eye view of the stack that we work with at CluedIn. And to give you kind of just a quick idea of what we'll be focusing on, obviously we'll be focusing on the graph structure and the graph data store that we're utilizing. And we'll also be on our processing, where most of our kind of analysis is done, where most of our machine learning techniques are applied, but also the good old techniques like text processing and standard text analysis, things like stemming and lemmatization and fuzziness and tokenization. It's all included within this processing pipeline. So let's wind it back around 5 to 6 months. We gave a presentation in GraphConnect London. And just to warn anybody who's actually seen this, this is not the same presentation. And essentially what we did was we were designing an engine that could build a decision engine utilizing Neo4j and machine learning techniques. And I guess like everybody in the room that's interested in machine learning, when you heard about these techniques like we did 4 or 5 years ago called machine learning, that we could add to our engineering tool belt, we kind of dove in head first and thought, well, how can this help us increase the precision of this problem of data integration done automatically? So we started out with using a library called Torch. And it's a C++ library. And we backed this with a GPU SDK called CUDA, mainly used for NVIDIA cards. And we started out with something called image object recognition. Essentially, what is in that image, the value, the business value behind that to get that metadata out is quite valuable, of course. And so we started out with a picture of me at my brother's wedding. And for everybody in the room that thinks, oh, that is magic, I'm sure there's just as many people in the room that are skeptical and say, well, to be honest, why didn't it detect male, human, eyes, glasses? And this is why this kind of field is very shrouded in a bit of mystery. And what you get used to when you're using machine learning techniques combined with the Neo4j is this terminology called false positives. So if we take our CTO is that classic looking Viking. Long beard, long hair, listens to death metal. When we placed his image through exactly the same process with exactly the same data models, it identified him as 97% a fur coat. And to be honest, I never blame the system for thinking this. It's really down to the amount of, or the data that it's trained on. And to be honest, I have no idea where bucket came from. So that's the more complex thing for me to understand. So what I'm trying to highlight is that machine learning is not this silver bullet. In fact, machine learning techniques' strengths is that it can help us elevate the precision of a problem like data integration that has been around for a very long time. And in the next 10 years, just new techniques will come out that will also never solve this problem. It will just increase the precision of the decisions that we're making on discrete, ambiguous data that could come from completely different data sources, could be structured, could be unstructured. I want to highlight one of the other important things that Emil also alluded to and touched on in his presentation, and that was the importance of context. You may have seen from our architecture diagram that we take a very polyglot design to our platform. There was a SQL database there was a blob store, there was a search indexing store, there was a distributed memory cache, and there was a distributed file system. Well, the graph, and specifically Neo4j, the reason why it was able for us to increase our precision so much in this problem was the idea of when you're analyzing data from this data store, it's one of the only data structures by design that maintains context when you're working on data. I mean, take the typical analysis problem. You load something out of a database, you put it into memory to do some operations, and then you serialize it back to disk. The graph database inherently lends itself to the idea of maintaining context once that serialization process is done back to the data store. Something that utilizing a document store or a relational store would require a lot of superfluous information, somewhat unnecessary, to achieve a similar thing, but in no way the same impact that a graph database could provide. So at the end of this research project that we had for around 2.5 years in how we could apply machine learning techniques with the graph to solve this problem of data integration, we came out with 2 champions. So 2 techniques that time after time as engineers we could rely on. We could be confident that they would be able to give tangible results that we could use time after time and release into a production environment where it could be automated. And that was clustering and neural networks. So clustering, of course, clustering algorithms have been around for a long time. And we used a couple of the kind of standard clustering algorithms you see a lot in the financial industry, banking industry, and so forth. So to cut that talk in London very short, what we ended up doing was designing a platform with this high-level design pattern, a recursive decision tree that allowed us to organically grow a graph, expand, collapse, and then learn. And I'll give you a couple examples of what that looks like. So what I've done is I have taken a couple of snapshots of what our decision engine has done in real time. So let's go to our saved searches. So some of the kind of questions we wanted to ask our data was, given very ambiguous data, trying to figure out information on an individual, how could you reverse engineer this to figure that out? So the first thing we wanted to ask was, okay, well, who is Emil Ephraim, right? So if we saw this data in structured or unstructured input, how could we enrich, clean, validate, deduplicate this data to be able to get some type of raw structure out of this? So one of the things that Emil alluded to as well was this idea of context, which is super important. The idea being that when you're working with your data, you're always working under some context, and that context in this situation is me. So I know a little bit of information about me, and essentially if I was to expand out this node, we have some very ambiguous information. It's not very defining or identifying in any way. Essentially, you've got my name and engineer. For Emil, you've got job title and name. And essentially, I've snapshotted what our decision engine looks like when it's running. And this is not a real-time system. This takes a lot of processing to actually achieve this. And so what you'll find you get is we're taking two discrete nodes within the graph, and we're starting to explode out all the internal data and the external sources that we can plug in that could allude to the identification of what are we referring to when we refer to Emil Ephraim as a person. So essentially what we're looking for is a big cluster of Emils right here, and as we go down, we're looking for a big cluster of possible Tim Wards here. And of course I have a very common name. Right, so the amount of noise and the fuzziness that could come from that is obviously a lot more than would come from someone like Emil Ephraim. But I just need to remind you, the key is context. When you're working with your internal data and using a decision engine, you're working in the context of your company's data. You don't have the context of the entire world, such as where Emil showed how Google has its knowledge graph. You know, it's working under the context of the entire world. This is what makes it a little bit more scalable. And essentially what you're looking for in your data is this kind of thing, where as soon as we explode out these different nodes and start to find overlap between two pieces of data, and to be honest, I'm super happy that it identified us both as a male, it starts to follow those paths more. And for the branches of the decision tree, such as these ones here, that don't have any superfluous branches, well, we start to prune those off. They're parts of the decision tree that don't get explored anymore, obviously to be able to contain some type of performance overhead. Of course, we could get explosion of data from this. We're trying to limit this. So call it entity reconciliation, call it entity disambiguation, entity linkage, entity merging. There's a lot of different names for it, but essentially this comes down to this classic problem of master data management. How do you infer connection or even merge two pieces of data out of what could be structured or unstructured? I mean, here's the classic case. I said before that the average company uses at least 30 different tools to solve different problems. If you look at the common company today or the common enterprise, you know that the data is dispersed. I mean, most people who are speaking here today would allude to that fact and concur with that fact. So how do you solve something like this? And what I want to highlight this time, because to be honest, you can go back and look online at that decision engine tree and how we presented that in London. There's a lot more detail there. What I would like to focus on is the 4 techniques that we spent the last 6 months on increasing the precision. So at London, we had 36 people sign up that day to our API and started throwing data into it. Obviously, different data from different countries with different industries. It's bound to offer different complexities. There's no generic way to really solve building data models in a very precise manner. And so I want to highlight 4 techniques that we use to increase our decision engine's precision that gave the biggest precision leaps. The first was pattern matching. And I don't mean this in the typical clustering type of finding segments in your audience and grouping them and just classic clustering algorithms. No, I mean pattern matching using Neo4j. The practical precision upgrade that we made was how do we solve decision explosion? I'll give you a really simple example that really happened in production, and that was if I want to know that if Neo4j and Neo Technologies are actually the same company. if I had in our precision engine or processing engine that it figured out, oh, wait a second, I have enough information now to merge these two nodes within the graph, possibly every other decision that was in that entire graph could have made its decisions based off not knowing that those two companies were actually the same entity. So how do you solve this in a way in a huge graph to stop decision explosion? And this same pattern is applied to how do you stop your processing applying itself to every node in the graph. And finally, the two machine learning techniques that we utilize, one is a supervised approach where we're using a clustering algorithm, and the other is using an unsupervised approach and how we utilize the neural network to be able to increase the precision as well. It's worth identifying that one of the key design principles to provide a solution like this is not about finding the best algorithm or the best solution for the problem and then going with that. It's in fact combining multiple different techniques to essentially solve the same problem and finding a mean weighting or a mean statistical confidence over all of those results to allow you to do something automatically. I mean, you can imagine the side effect of being able to integrate two discrete pieces of data sources and there's merging and inferences that are made that are just not true. That requires us to use statistical models to make sure that we are only making merging decisions over a certain precision threshold. And it really depends on the type of data that you're trying to merge. For something like people or persons, they need different thresholds of confidence to be able to merge two entities within the graph rather than something like a project or a document. There's a lot more personally identifying things about an individual, but there's also a lot of ambiguous and fuzzy properties that exist on a person that make it hard to find inferences between these two pieces of data. So let's start with pattern matching. How do we use Neo4j and their pattern matching techniques to increase the precision of merging data automatically? To understand this solution, first we need to look at another. The supervised precision that we increased. So entity reconciliation, it's the idea of being able to take two pieces of data and figure out if they're the same or if there's any inferences or relationships between them. So we have a classic example. Our system has integrations or crawlers that go out and get data. Fortunately, most of the SaaS products that are modern today support real-time data, i.e. sending data to us directly instead of us having crawling mechanisms that go out periodically and poll these systems. One of the design principles behind CluedIn, and if you're wanting to solve this problem yourself, I would also highly suggest, is in the fact that we treat every single piece of data that we get from any system as possibly right or possibly wrong, i.e. they are one clue and only multiple clues combined in certain ways, run through multiple different processing techniques can make us actually figure out if there's a fact there or not. I mean, take a look at your classical 20, 30-year-old company. They're not using these modern tools, a lot of them. And the data in there is completely dirty, has been just neglected for years. A lot of companies do need to go through cleansing processes, of course, but this is not always the case. So this design principle in solving entity reconciliation and taking every single piece of data as potentially wrong or right allowed us to be able to increase the reliance and the confidence of the results we're doing. A side effect is that this can never be real time. There's a lot of reconciliation that needs to happen. And so this is a classic example of the type of entity we would receive from a system like this. This would be something like a CRM. So we have some first names, some last names, and some other identifiers. Now, if you go back 2 years in our platform, we had designed a huge rules engine. A rules engine that would have things like, well, if you're trying to merge two people and their first names are the same or within a certain kind of fuzziness threshold, or utilizing string distance algorithms like Hamming distances between two names, are they within some acceptable threshold to cater for things like spelling mistakes, putting dirty data in, importing from a bad Excel sheet that at its core was already dirty? Now, of course, there's a point where this doesn't scale. Because if you came up with these rules, such as, well, if the first name and they're in the same country and they worked at the same workplace and their job title was the same, okay, well, in some ways, that's 77% possible that that's the actual same individual. So machine learning techniques are the perfect candidate to scale this problem. The classic case of, I know I'm generalizing this in this way, but one of the great things behind machine learning techniques is that no longer engineers have to define rules to get answers. It's that the data that it's trained on will reverse engineer the rules for us. And so at CluedIn, to solve this problem, we used a clustering algorithm that falls under the machine learning banner called a random forest. And it's actually very easy the way that it works. The implementation is not necessarily hard, and to be honest, most libraries today come with these out of the box, so it's not really an issue. I just want to explain how it works and the huge amount of precision gain that we got from automatically merging two pieces of data. So essentially the way it works is that you take a sample of one of the types of models in your data. Let's take people. And you highlight properties or features within those entities that would usually, in a fuzzy approach, lead to the identification that they are the same node. I don't mean personally identifying things like emails. We can be a lot more statistically confident that, well, if the data seems like it's consistent wherever it comes in, it's the same email address, that's easily enough for us to say, yeah, these are actually the same person. It's where it comes down to these combinations of, well, if their social account is this, and that exists within their email address, and their first name's this, and all of these rules that you would have to manually write, this is where a random forest algorithm can do that work for you. In fact, this rules engine in our system has been completely removed and replaced with other techniques, including this technique. So back to pattern matching. Once our entity reconciliation engine has decided that it will go into a merge operation, so it's figured out to some statistical confidence level, and we use just a simple confidence function called the Pearson's chi-square, which is used a lot in the space of things like multivariate testing on websites. If there's two variations of a website, which one actually is more performant than the other? Pearson's chi-square is a very popular one that's used in that space, but it can be used as a generic statistical model as well. So once this entity reconciliation engine has been given the tick of approval from the previous random forest approach, what it does is it takes that graph that I showed you before where there was an explosion of Emils and an explosions of me. That sounds really weird. Sorry. And it tries to figure out, okay, so I'm going to try and do a merge operation on the green arrow down to the Emil down the bottom. Sorry if you can't see that. And I'm going to do a merge operation on the blue Emil where the arrow is pointing. Okay, so once that operation's been done, it's past the statistical confidence. What we do is we now store the patterns of the connections around that node to be able to feed into the next part of our processing pipeline, which is if two nodes do not merge, or if they do merge, what are the patterns around those pieces of data? This means that we can use this as a model as well to figure out, well, okay, if our random forest didn't work, if we look at the storage of all the types of patterns that would usually lead to a merge or not a merge, do they overlap? i.e., if we found that we weren't able to merge these two amines, what we would look for is we would say, okay, well, statistically, how much data when it has stored connections like this, and I'll just explain this is a proprietary type of format because we can compress it a lot easier, is you've got one incoming connection to a person, a one incoming to a location. We're using this, and this is one of the big things that sums up machine learning. It's never about right or wrong. It's precise to a certain level. And I just want to reiterate the fact that this is not something where you would say, okay, let's move to this because it had the better precision. Let's get rid of every other process we use to figure out relationships between data. No. I mean, it starts off with cleaning your data, having text analysis on it that prepares the data to be put into systems like this. So then how did we solve decision explosion? So I describe decision explosion as the idea of, in theory, if you merge two nodes, those two amines, it's potential that every other node in that graph made a merge operation that was successful or not successful based off those two nodes not being merged. So how do we stop one decision causing the entire graph to be touched and in turn the entire graph to go through a merge process? This actually did happen in production, and essentially it came around the idea of this idea of dirty data. We had one customer that had plugged in a network drive, and they didn't have a CRM, but they had Excel sheets that had all their customers in it. And one of the engineers we were working with had replaced the first name and the last name of all the users just as a test. You know, they just accidentally just Excel copied and duplicated the first name and last name all to be Jerry Nielsen, I think it was. And in the end, what it did, it went through and it said, well, okay, now I've got data that's giving me identifiers that every single person in your system has the same name. This caused the entire graph to go into this kind of heavy processing and, to be honest, Stack Overflows where the Neo4j memory heap was just absolutely bombarded with the idea of the whole graph basically had to be loaded into memory, which of course it couldn't. But of course the heap stack overflow made Neo kind of fall in its path. So the way that we solved this was in a very similar way that we solved the path triggers, or the path traversals, or the path patterns, or the pattern matching that we did in the previous step. So during this entity reconciliation process, we would store basically for all things that didn't merge. Why didn't it merge? What other nodes in the graph could lead to the fact that a merge would happen? And so something as simple as, well, if those two amine nodes both had a position, or both had a company that they worked at, or both had a birthplace that they had were born in, this might be enough to actually be able to merge this. The problem of this being that you would need to scan the entire graph every single time that you needed to be able to do this. So we solved this in a similar way, where whenever we would go into a merge process and we would realize that these two amines were not going to merge, what we would do is store the patterns that we got from the previous step of what would typically be used to merge these two things, and then we would store the delta. We would store the delta on the actual node itself, just in a string property. Of course, we made sure we indexed it as well. So when we were doing these lookups, when a new node would come in and it would be connected to a meal, instead of doing these table scans to figure out all possible operations that would maybe need a merge operation with this new input, this new information, well, now we just have it in an inverted index, which is, of course, much quicker to look up and process. So finally, and probably most importantly, because it gave us the biggest precision leaps, was our use of a neural network. So there's different types of neural networks that you can, of course, use to approach this problem. And they're summed up into multiple different levels. And kind of I guess the popular ones are the convolutional neural networks and the recurrent neural networks. And I mean, I'll just say this anyway, I'm not sure how many data scientists we have in the room, but essentially one of the core principal differences between the two is that, well, one is actually working at better that's data that's spatial, that keeps space in mind. And the recurrent neural network is something that kind of keeps time in mind. So when did this data come in? When was it discovered? When was it created? All of these types of aspects. So when you're using the neural network, in fact, the biggest challenge we had was figuring out what parameters do we actually feed into this neural network. So a neural network, just at a high-level summary, is broken up into different layers. We have layers that are responsible for making different decisions. And they're all connected to each other. And one of the benefits of the neural network we chose, which was a recurrent neural network in the end, was its idea of backpropagation. What this means is that data that's fed in from one layer to the next layer, the output of those layers could actually be fed back in to the existing layers to be able to make better decisions or to learn from the decisions that it's made in the past. So now that we kind of had the right neural network approach and we had decided the right pattern to use, the biggest problem was what do we feed into this system? And we tried out with multiple different things. In fact, we started out by using the depth of the graph. I.e., if we have two nodes, what's the depth between these two pieces of data, and using that to train our system. It just led to two ambiguous results. It just didn't lead to good precision at all. And in fact, the best result we got in the end was from using similarity functions. So one of the ones out of Denmark, one of the guys is Danish, the Sørensen dice coefficient. These are all similarity functions or distance functions. They can be applied to figure out what's the distance between two strings, what's the distance between two hashes in a very kind of course, performant way and low memory impact way. And so we started out with a dice coefficient and fed this in as our as the parameters to our recurrent neural network. What we found out was actually that like we had made the design decisions in lots of other parts of our system, then in fact the key was to use different types of hashing algorithms, of distance algorithms. They were the things that we had on the different levels, i.e., if dice coefficient gave us a certain float score, or float value, the next layer would be the result from the Levenshtein function. And essentially what this is doing is utilizing this backpropagation that comes from using a recurrent neural network. Decisions that were made on the first layer that passed into the second. The second layer's output could feed its output back into the first layer. That's where the learning mechanism comes in when you're using a neural network. And what I mean with the similarity functions is, I've kind of already alluded to this, is that when you're taking two types of models in your Neo4j database, such as people or companies, essentially what you're looking at is identifying the features or the properties on those nodes that can lead to some type of overlap in a fuzzy manner, not an obvious identifying manner like an email. In fact, they will skew your result a lot if you highlight things like even phone numbers to some degree or emails as one of the features that you're using in your entity reconciliation. So 6 months ago, we released this at London GraphConnect. And we've spent the last 6 months on, of course, learning a lot. We're running right now with 280 million nodes in the graph and close to 1 billion vertices or edges. And trust me, there is a lot of learning that actually comes from that. A classic case that we always bring up was we brought on our first customer in the food industry over the last 6 months. And because of our models that we train are trained off certain people's data, it's trained off generic models, it's trained off the context of a user's data. What we found is that for their account, that it started identifying people like spicy chicken and lamb korma as a person. And once again, I just want to reiterate that welcome to this space of machine learning. It's fraught with error rates. It's fraught with this kind of magic, mystic idea. And I guess what I'm trying to say is that the way that machine learning helps with Neo4j in being able to connect data automatically is in its ability to combine machine learning techniques with things like the standard pattern matching you get from Neo. Of course, some of the standard kind of coefficient algorithms you get in Neo, the shortest path algorithms you get in Neo, classic text analysis like tokenizing and stemming and lemmatization and all of these that are typically used in the search space. These all combined together, although result in something like finding out if Emil and myself are connected in some way, is something that's not done real time. It's done with a huge amount of processing. And the way we kind of like to say it is that when you're trying to merge data automatically between systems, it's not so important that the data is served to you in real time. It's important the integrity, the quality of the data is maintained, no matter the type of data that you plug into it. So as an engineer, here are some of the reasons why it might be interesting for you to try this out and join the multiple companies that are utilizing this in production right now. And that is that all of the data that you push through to the API, you get the data cleansing, you get the data enrichment. One of the really interesting things is you get this polyglot persistence. The idea that Emil kind of alluded to as well is that, you know, Neo4j is fantastic at doing joins across huge lengths of connected data. It's also good at reverse engineering how two nodes are related to each other. It's fantastic at pattern matching. But guess what? Relational databases are fantastic at aggregation. They're fantastic at doing set-based operations like groups and summing and aggregates and min and all of these types of set-based operations. And then finally, for those of you who are interested in the machine learning space and working in that space, you will know there's a lot of different libraries like TensorFlow and scikit-learn and Spacey and all of these text processing and also clustering and machine learning libraries. Well, the great thing is that most of these libraries actually export into a common format, and we also support that. So the data models that we build up for you can be exported. You can plug them into systems like TensorFlow and continue to learn in building internal applications in other parts of your business. The reason it's interesting for companies per se and not just engineers is this idea of, you know what's one of the fascinating side effects of having all your data in one place? That getting the visibility over what's happening at your company is much easier. And for problems that are inherently, technically, very hard, if not, you didn't hear it from me, impossible to solve, like the data regulations we have in the EU, it makes it that much easier to reach this type of compliance, knowing the extreme amount of fuzziness. And the classic case is, in one system I might be Tim Ward, in another system I'm Timothy Ward. In another system I don't have my name, I have my personal address, I have my private address, I have my work address. To figure out the linkage requires techniques like Neo4j and that data to be mapped, combined with machine learning techniques as well. So I am spot on. Still 30 seconds. So that's me. Thank you very much. I'll take any questions if anyone has any.